Hello, greetings, greetings. Okay, this is for Physics 102 for the fall of 2021. This is a video recording of the second part of the thing on a spring discussion. That is, I'm going to continue going over homework 1, picking up from question 4 of homework 1, because we got up to question 3 in the class last week. This is to compensate for the 75 minutes of time or so that we missed last week. This won't be quite 75 minutes long, but it'll be close. And it will be assumed that you've seen this by the time we resume together this Wednesday at 3:05 p.m., Wednesday, the 29th of September. So, okay. So again, this is Physics 102. This is the video that I asked you to watch in preparation for the end of September of fall of 2021. Okay. We were up to, well, we had just done question 3 on homework 1, a thing on a spring. That's where I'm going to pick up from now. So okay. Question 4 asks, at the equilibrium position at x equals 0, what is the instantaneous speed attained by the mass, having moved in from an initial position of x equals 0.15 meters. Now, just to be as clear as possible and as comprehensive as possible and so forth, what we're going to do here is do the whole process of solving problems as I'm requesting you to do. That is, in principle, every single problem we solve, we begin with a diagram and a fact pattern, then we state the question, et cetera, et cetera. Now, for the record, again, like there's one diagram and fact pattern that applies to all the parts of this problem. I mean, as the sheet was presented to you, homework 1, there's a diagram at the top, there's some facts, and then you're asked a series of questions. When you do homework, or when you solve problems, or when you turn in an exam to me, or when you do research in the world, or you submit a journal article in the world, like, it is understood that a whole series of sub-questions might be asked about one and only one fact pattern, one and only one diagram. I am not actually suggesting that you have to redo the same diagram and the same fact patterns every time. You should make some reference, like for a question 4 now, you should say see above for diagram or for a fact pattern. It's like everything should always stand on its own independent legs. Everything should always be independently readable, independently clear, self-sufficient physics. So on the one hand, I'm not suggesting that you literally have to redraw a diagram every single time you do a new part of a question, but there's no harm in doing that. And since I haven't seen you for a week, and since we're starting midstream here, I'm certainly right now I'm going to draw the diagram again, and I'm going to tell us the fact pattern again right here, even though we're at question 4, and I'm going to ask the question 4, right? So I'm trying to produce a document here. I'm trying to produce a document here that would make its own physics sense, even if it had no prior context, even if you had never looked at question 1, 2, or 3, or didn't have the sheet in front of you, right? And I mean that partly because, I mean, this is like a flying abstract video on its own. Like, who knows? This is coming out of context. So it really makes it easier for you, hopefully, for me to provide you with everything right here and now as a like one-off, right? But also I can't urge enough to you that it is good practice to do that. Sort of treat everything like an HBO show. Like, sure, the show is that, like, I mean, an episode of an HBO like show, you know, like an episode of The Sopranos, or an episode of, I'm so dated, I can't even think of what the examples are, but like, or 6 Feet Under, or whatever, right? I'm saying, like, what's brilliant about these big TV shows that now exist that are sort of more cinematic than old network TV used to be. What's brilliant about them, sidebar, but what's brilliant about them is that every single episode you watch is that much more rich and entertaining and robust if you've seen all the prior episodes and you know, or Breaking Bad or something like that, right? Like every episode you watch is better. Certainly, there's a lot more to get out of it if you've seen all the prior episodes and you know all the storylines and all that. And so they do try to hook you, and you do want to watch them all as part of a larger whole. However, they're all written so that anybody can tune in at any time and just watch one of those episodes and not feel alienated or lost or bored, right? I mean, analogy, examples. But I'm saying for a reason, that's the way physics should be. Like every piece of physics should be a piece of physics that doesn't require like a background understanding of whatever conversation the teacher and student happen to have been having. So I'm going to attempt that here. That's what physics, every piece of physics homework should be its own little mini legitimate physics proof that makes sense on its own and can convey some general truth about physics, irrespective of the academic context. Okay, so what was our context here? It was so all of what I just did is what I'm considering to be, step one, diagram and fact pattern. I think you should do that for every problem you solve or every, submission you make to an exam or whatever, right? Then I'm saying the actual question at hand for question 4 was at x equals 0. What is v, right? That's the question, right? So, I'm putting it down. And another way of putting this is we should be able to follow what I'm doing. Like I should be able to follow what I'm doing. You should be able to follow what I'm doing, even if you don't have the homework sheet, the actual problem set next to you. Now, I mean, I think you should have it next to you. I think you should get to know it. But, that's for reference and for clarity and all of that. And you should also be looking at whatever work you did, to compare. But just notice I'm giving us just enough information that I don't have to look anywhere else in order to do this now. Like from here, whatever solution I'm embarking on now should make sense just based on this, right? I mean, that's the idea. Okay, so I've done diagram fact pattern. I've done what is the question going to the next page here. I'm going to start answering the question right now. I'm just repeating the question just so we see what we're doing. So the question was okay, just a quick reminder. I mean, I think this is clear from the context before, but the whole point is that a mass was on a spring the mass was held there at 0.15 meters from the equilibrium position. All right, let me even back. Well, yeah, from the spot at which the mass would be stable. In other words, let's start all over again. We have a spring here. It's attached on one side to a wall. Before I put a mass on it or do anything to it, it has a certain length, a certain rest length, a certain equilibrium length, a length that it just sits at undisturbed and untense when nothing is being imposed upon it. Then we put this mass at that unstretched, relaxed length, wherever that spot is that we put the mass on, wherever that edge of the spring is, we call x equals 0. Like by definition, 0 refers to the equilibrium edge of the spring. But then we pull the mass back and we hold it at a stretched length of 15 centimeters from equilibrium, right? We hold it there and then we let it go. So the spring force, the elastic force, the restoring force, the Hooke's law force of F equals negative kx starts pulling the mass in toward equilibrium. So there's a force on, and no, there's no other forces acting on this mass because we let it go. So the only force acting on the mass is a leftward pulling elastic force. Since there's a force pulling to the left, the mass begins to accelerate to the left. We found out the values of those numbers in parts 1 and 2. The mass starts accelerating toward the equilibrium position and moving toward the equilibrium. But more to the point, it starts accelerating toward the equilibrium position. So it gains speed, it gains velocity. Having started at an instantaneous velocity of 0, it builds up velocity. And by the time it gets to the equilibrium position, it has a lot of velocity, right? Like it may be trying to get to the equilibrium position, and the equilibrium position might be called an equilibrium position. But as we sort of found out in parts 2 and 3, equilibrium position doesn't mean that the mass stops suddenly. What makes it equilibrium is that the mass will have no acceleration there. It means that the forces are balanced there. In fact, I want to say this right now. Just to be as clear as possible, equilibrium in physics, and therefore truly in all of science, but you might not have thought of this before physics. In physics, the place of equilibrium is not a place of no motion. It feels like it should be that often. People think that often. Oh, it's equilibrium, so it's not moving. That's not what equilibrium means. Equilibrium means equal, means balanced, means the forces are balanced. Equilibrium is where all forces are balanced. Therefore, the net force on a system is 0 at equilibrium. Equilibrium means the net force on a system is 0. But therefore, by physics, by Newton's second law, that means the place where acceleration is 0. It doesn't necessarily, and it frequently does not, mean that the velocity is 0 at equilibrium. Things don't have to be at rest at equilibrium. They have to be not accelerating, which means two things here for our context. One, what that means in general English terms is it doesn't mean you can't move through equilibrium. It means that if you happen to be not moving, then you'll continue to not move, right? Equilibrium is the place that if you put something there, if you put the mass at the end of the spring at x equals 0 and let it go, nothing will happen. As opposed to any other spot where if you like hold it at 15 centimeters and then let it go, then it starts moving in, right? So equilibrium is balanced in the sense that if you place something there, it will continue to stay placed there. which is again to say acceleration 0. It won't change its velocity. But if something is moving through toward equilibrium, like it is here, something's gaining speed, getting faster and faster, moving toward equilibrium. When it gets to equilibrium, okay, it has no acceleration. It will have an A of 0. But that means if it already has a V, if it's already moving when it gets there, since it would require an infinite acceleration to suddenly crash land from a high velocity down to 0 velocity. It would require like a cartoon kind of, right? But there is no acceleration at equilibrium by definition. So if this thing is moving and toward equilibrium, I just want to make it absolutely explicit to all of us that when this object, the mass on this spring, arrives at equilibrium, even if we want to think that that's its goal or its destination or something like that, when it gets to equilibrium, it's going to freaking keep going, right? It's going to have a high speed at equilibrium, and it's not going to be able to lose that speed immediately because it doesn't have any acceleration. It doesn't have any, or deceleration. It doesn't have any change in velocity. Therefore, it will keep going through equilibrium for a while on the other side. Like the spring will begin to compress, okay? So the high speed that this object will attain at equilibrium is not a contradiction in terms or not anything unusual. We should expect that this mass will have a considerable instantaneous speed when it reaches equilibrium. We should expect that. And B, that number that we're solving for, that non-zero, I mean, that number that we don't know, that non-zero number, that's what we're solving for here. We're solving for the non-zero instantaneous speed that this object will attain the moment it reaches equilibrium. Like that's what we're solving for, right? Okay, just to make that clear. So okay, just to make that clear. Okay, so how are we going to solve that? We're looking for living now all the wrong place. We're looking for a velocity. So often in old physics, in like stage 1 of physics of last semester or something, we might say, oh, we're looking for acceleration. We're looking for a velocity. Well, let's like use acceleration. Let's use something like x equals 1 FAT squared plus v naught t, or like v squared minus v naught squared equals 2ax, or something like, let's use a kinematic thing, kind of like we were doing for the first 3 questions, or like some F equals ma thing. We might think that, but we can't use kinematics. I'll write this down. Whoa, sorry, did I just lose? Yeah. Oh, I did. Pardon me, I just lost the screen. Hold on 1 second, I'll bring it back. Hold on. Back. Yes. Okay. Okay. So quick note also, like we're looking for a V. we're looking for velocity or speed, right? We're looking for the magnitude of instantaneous velocity. In the first three questions on this sheet about springs, we considered motion and forces. In other words, we used the first two chapters of physics concepts in order to solve. And the first two chapters of physics are always true. Like anything we ever believed about A or B or F's or F net equals MA, always true in physics. So always a good first instinct in order to solve any problem. And so we might consider them. We might start writing down some equations like we just were in parts 1, 2, and 3. We might write down something like A equals V minus V naught over T. I don't know, something. But without me wasting too much time writing, but we'll find if we start writing down equations, we're going to run into a jam. It's not that the equations are going to be false. It's that they're not going to do anything for us because, because I gotta write this clear. I'm sorry. This is too important. Always my most important things. I always what I squash at the bottom. It's terrible. Okay, to make it clear here, sort of big physics problems have we pointer, like, because first things are always first. And again, just always remembering, like, as physics gets deeper and deeper, people tend to always, I don't know why that says that there, but okay, people tend to know how to run the equations and run the math and run the algebra, but they often will say, especially as things get thicker, they'll say, well, I know what to do when I know what to do, and I can follow what you're doing in class, but I never know how to start a problem, or I never know, in other words, which equation to use. If you tell me what equation to use, then I can do the physics and blah, blah, blah. People often say things like that. Now, let's recognize, first of all, that means you know how to do math, but you don't know how to do physics, if you say that, or at least not. You can't really say I know how to do physics when you give me the equations. I know how to plug in, but I just don't know which equations to choose. Which equations to choose is the art of physics. And 9 times out of 10, when we're really doing physics, we're not choosing equations, we're developing equations. But if we're trying to get used to and trying to get better at how do you know what to do when, my first advice is always start at the beginning and work your way up. Like, you should always try the simplest, most true thing first, such as kinematics, definition of average velocity, average acceleration, and then forces, like go in the order that the chapters of a physics book go. Try F net equals MA next if you don't know what to do. But here in this case, we're going to have to try something even further than that. We're going to find that the method that worked in problem 1, 2, and 3 will not succeed for us in problem 4, and its failure will naturally lead us to realize what we should be using. What I'm trying to say is, we can't use F net equals ma or like A equals V minus V naught over T or something here, because if you think about it, even though the nature of this problem is we have a force that is changing every single place that the mass is. Like we don't have one F to plug into anything. And therefore, since F net equals ma, we don't have one value of A to plug into anything or everything. Any equations with A or F's in them, we don't have an A or an F to plug in. And it's not just that we have more than one to choose from. It's not just that if you look at your answers from questions 1 through 3, you'll notice that A at the initial spot, A was like 100 or negative 100 meters per second squared. And then A at the equilibrium spot was 0 meters per second squared. So first of all, I'm saying, look, well, which one would you choose? If we do any equation that has an A in it, which A would we be talking about here? But more to the point, it's not just that we have a choice between two A's. It's that A wasn't jumping like a cartoon from negative 100 to negative 50, like to 0 or something. A was smoothly, continuously varying as the mass came in from the outermost position to the innermost position. Every new position that the mass occupied, there was a new F and therefore a new A. F was varying as a continuous function. Okay. And I'm going to go one step further here. So first of all, that means I can't, that calls for more powerful or at least more efficient physics. The fact that we don't just have one F or one A to plug in. But more specifically, whenever F varies as a function specifically of position, that is, I'm not just saying that A is changing in time. If A were changing in time, that's not so hard. Then like we could just take a derivative of A or something like that, if you follow me, and do some equations with that. But it's not that, but time is not the independent variable here. I'm saying that for every new fresh X, there's a new fresh F and therefore a new fresh A. So F is varying as a continuous function of space, not of time. Whenever that occurs, that is a signal for us to consider the concepts of work and energy. Like, let me, well, I'll be more, well, yeah, like, so we're going to use work and energy here, as many of you did in the homework. And I know that you may not have consciously even known why. It might have been a lucky guess or something, but I'm telling you why, like the time to use work and energy. But if notice, like you were using F net equals ma and like F equals kx, negative kx for the first 3 questions. And then even if you got this right, which is great, I mean, especially if you got this right, you somehow, something in your brain or your soul knew to shift all of a sudden to energy methods. I'm not sure if you like, think about like, why did that happen? Why was that okay? Why did we suddenly abandon one ship and jump into another? The reason is because because of this. whenever, so there's a problem solving. I mean, this is a statement about the universe, about the world, but it's also a statement about problem solving. Basically, whenever you have a speed spot relationship, whenever you have a speed spot relationship, like as opposed to speed time, whenever you know the speed at one place and you wish to know the speed at a different place, or some version of that, like you know the place at one speed and you wish to know a different, you wish to know the place at which the object will attain a different speed. Like whenever it's a speed spot correspondence that we're talking about here, and particularly if we know in advance that forces are changing from one spot to the other. I mean, if forces are changing or acceleration is changing, then you could just use constant acceleration. But basically, when we don't have constant acceleration, when we can't use our constant acceleration equations, when the acceleration and the force are changing from spot to spot, and we know the speed at one spot, but we want to know the speed at another spot, that's when we move from a consideration of forces and kinematics to a consideration of work and energy. Like this as a problem-solving technique, think of work and energy whenever you face a situation. Now, why or how? The following. Okay, I'm going to read this out loud because the handwriting is. Sorry. Now I'm saying a lot here. This also goes back to the question of last week. Okay, and this is going to get it. I don't know if you can read. Well, let me read out loud what this says. But let me read out loud what this says. Work is defined to be, like triple equal sign, right? Work is defined to be the definite integral from x1 to x2 of the force with respect to displacement. Like work is the integral of f dx, the integral of, it's the integral of f treated, 1 second. Okay, let me assume, well, it's gonna take a while to, well, something's going to pop up on the board in a second, but assume that you have some force that is some kind of function of position. There it goes, right? Could even be a simple constant function of position, or it could be complicated, but you have some force that is applied from one position to the next, to the next, and the, so I have a box on a table and I'm pushing the box across the table with my hand. So my hand is exerting a force, a normal force on the box, and the box is being displaced across the table, right? So some situation like that. And how hard I'm pushing on the box like depends on where I am on the table. Maybe even depends in a trivial way. Maybe you're like, I'm never changing how hard I'm pushing. But so if you assume that I push with some force, capital F, which is a function of position, lowercase x. So you assume that force is the dependent variable and position is the independent variable. Then technically speaking, mathematically speaking, generally speaking, or I mean, like universally speaking, what we mean by work is how much force you exert along that whole displacement, the integral of force with respect to displacement from the initial position to the final position. Work is a definite integral of force throughout displacement within a finite specified region from one, initial position to some final position. So technically work is the integral of force with respect to x from value x1 to value x2. Now that's what work is. And in fact, I'll even say technically. And that's what work really is, whether you've seen that before or not. Work, if you understand integrals, then you might understand work at some level. If you understand, the better and better you understand work, I'm going to ultimately tell you, the better and better you're going to ultimately understand integrals. If you have any knowledge of integrals at all, then this definition might mean something to you. Whether or not you have any knowledge of integrals, this definition is true. But now we get into Kazi's, I believe it was Kazi last week, who raised a very fair and important sort of concern or consideration about like, what's the role of math in this class, and particularly calculus and stuff like that. And I went on a whole big romp and frolic about that last week. Let me just try to continually keep that in mind as we talk about things. I mean, I love math. It's sort of hard not for me to talk about math somewhat in the context of physics, but here's the deal. What work is an integral. Do I think in my back of my mind that many of you have seen integrals here and there before? Yes, I do. Do I expect or do I demand that you have a firm grasp of integrals in order to be in this class? Absolutely not. Do I know that some of you have never seen integrals? Yes, I do. Is that a problem? No, it isn't. Do I think that those of you who have seen integrals love them or feel comfortable with them? No, probably not. I think there's many of you who have seen integrals and hate them or feel like that they shed no understanding on things for you at all, at least at this stage. And there are so many of you in the class that even if you have, or maybe even especially if you've seen integrals, if I introduce an integral right now and say that's the meaning of some physics concept, for some of you, it'd be very fair if you'd be like, oh, well, that's great. You just made it worse. Like you didn't explain something. You just suddenly gave me like a headache. I totally get that. And I was there as well. I definitely was in that place where the minute someone would bring in an integral, that would only make my understanding more cloudy, not better. And it would also make me hate life. I recognize that. What I want to say is part of my goal is eventually to get you to feel better about integrals and to see them in a more clear light through the lens of physics. Okay, so I'm not going to resist the temptation right now of saying to you, before we go any further, what work really is the simplest possible integral of force. It's the integral of force with respect to position. It's the integral of force over a space, like as opposed to over a time. Okay, what work is the simplest possible integral of force with respect to space. Just bear that in mind and bear with and indulge me in writing it down, because the deeper we go in physics, the more we see work and stuff like that, the more you might what might start falling into place for you is actually what an integral is. And I am going to talk about that. However, I'm also going to say, so that's why I'm saying it, so we can start connecting the two together. However, now back to reality, like let's assume for the moment that you hate integrals, so you don't know anything about them, or that this line up here doesn't do anything for you. Again, please also notice it's a triple equal sign. It's a definition. It's not meant to be an explanation. It's just a statement of relation between math notation and physics concept. Okay. And by the way, anytime you integrate something and you make the independent variable space, like notice again here, our independent variable is dx, the variable is x, as opposed to saying dt or something. If space, position, is your variable, and you take an integral with respect to that, in physics, that's called, or actually in math and physics, that's called a path integral. You're integrating something along a spatial path. Okay, so I am asserting right now that from here on in, I want you to think of work as the path integral of force. Now, but what does that mean? What does that mean? And also, I'm watching the clock. We're not going to go all day on this, but this is like, again, it's good background to have before we like dive into the next class. Yes, and I am watching the time. Like, what does that mean for us right now? In simpler terms, what I'm really saying is work is force times displacement. And you've probably heard this before, maybe in a prior physics class, or maybe in 7th grade or something like that. Like, look down, like I'm saying, oh, I should actually, one thing. Well, not yet. I mean, I'm saying down here, sorry. I'm saying what work is over a small but finite interval. And let me even, I want to put that somewhere. You should write this, if you're listening to this video at all. I don't want to cram this page any further. I may write this on the next page, but please note that whenever that triangle, delta, yeah, I am going to write it here. So this is, okay, this is a bit hideous. I'm saying from now on, delta, that triangle, what that always means in math and physics. I mean, you've seen it before. You might think delta means change. I mean, it does mean change, but I think a better word for that is difference, like delta, difference. And yes, like in the context of delta y over delta x means the same thing as y2 minus y1 over x2 minus x1, which is slope, right? Like you've seen this in that context before. What does delta really mean in general in physics and math? It means difference or change, but specifically it means a small but finite difference or change between two values of a variable. Whenever we use delta, we mean it to be like a small but finite interval or segment or region between two values. So I'm going to say right now that delta W, meaning work over some small but finite region of space, okay? The definition of work is force times displacement. It is that. It is force times displacement. When you want to really think about what is work, It is how hard you push something through a space. It's not just how hard you push it, and it's not just how far something gets. It's the product, both mathematically and sort of physically. It is the consequence, the result, but the multiplication of the entire product of how hard you push something in newtons times how far it goes in meters. It's kind of like saying, so it's multiplication in the sense that, and why is it multiplication, or what are we getting at with multiplication? Well, we're getting at what the property, what the relation of multiplication implies, which is 0 times a number is always equal to 0, right? So if I don't apply any force at all, I don't care how far something went, no work was done. If I push something really hard, but it doesn't go anywhere at all, so F could be really high, but if delta X is 0, then the total product, the total multiplication, the total effect is 0. What work is, and that's what we want here. We want something that if you have bigger force and or bigger displacement, you get a bigger product called work. What work is the effect of a push through space. It's like if you're calculating how many newtons of force you applied to something through how many meters of space, what you're really asking is what's the accumulated effect or consequence or impact of all this force as it was applied or exerted through all of this space. That's what you're asking, okay? And so okay, so a joule of work is the accumulated effect or consequence or impact of a newton of force acting through a meter of space. Okay, and I guess all this maybe is sort of obvious, but well, I don't know if it's obvious, but it's true. And so in simple terms, I shouldn't say in simple terms, in simple situations where you have, excuse me, a known force acting through some given displacement, you simply multiply the magnitude of that known force by the magnitude of that displacement. And what you get is this quantity called work, measured in joules. A joule is a newton times a meter. Okay. That's what work is in small but finite intervals of space. The only reason I have to Okay. What I want to say right now, and we will probably get back to this together as a group in class, but what I want to say right now is the calculus always comes in when things are changing over intervals of space or time that are either infinitely small or infinitely large. Like calculus comes into play once we're dealing with infinity. Frequently, it's infinitely small. That is to say, calculus comes into play when we have a change, where we have, say, a change in force, and where the change is not in steps or stages or staggers, right? Like the fact that the force doesn't go like negative 30 newtons, right? Negative 29 newtons, right? Negative 28 newtons, right? Like if the force went literally like in steps like that, in staggered, quantized, countable, discrete stages, then we might have a really annoying, complicated situation in our hand, but we wouldn't have a situation in our hand that required calculus. If we wanted to calculate the work that the spring was doing on the mass here, we would simply say, oh, for the first, like even if the force was doing this wacky thing of changing in stages, we would simply say, oh, in the first stage, when the mass moves its first centimeter, the force is, hello, did I just lose? What just happened? Wait, excuse me. Oh, someone is here. Okay, sorry. Interesting. Okay, pardon me. We're going to end soon, but did I just lose the video and why? Hold on. I'm sorry. Hold on a second. I don't know what just. It's weird. Hold on. Sorry. Huh. I don't know. I don't know why the video is lost. I guess it doesn't matter. You're not really here to see me. You're here to see the board. And we are going to wrap soon. Sorry, something funny is happening. Anyway, we want to know the work. We want to know the work done. Like work is force times displacement. If nothing else, if there's no takeaway so far, and is just that work is force times displacement. And maybe that's totally review. Maybe that's old news. Maybe it's not. But 1 joule of work is 1 Newton times 1 meter. If there's nothing else so far, that's what we're saying. But now but so why do I have to bring in calculus? And why is my life so complicated? Because basically we have situations where we don't know what number to use for the force number to multiply by displacement, because we can have situations. Well, all right, let me just write this down. Okay, well, I'll just read this and say, and we will be wrapping in about 6 minutes, but I'm saying if you have a small displacement where the force doesn't change much, like where the displacement is small enough that the force like doesn't really have room or time to change much. So you have one value for force and you have a value for displacement. You just multiply them together, and that's your amount of work that you did. I still haven't told us what we're going to do with that work, but if work means force times displacement, then as long as the displacement is small and the force, as long as the displacement is sufficiently small, the force will be reasonably constant. So you take the constant number for force, you multiply it by displacement, you have work. End of story. Now, if the displacement starts getting large, and that is the case here with our spring, if the displacement starts getting large and the force starts varying, which is the case here with our spring, right? We don't just have one force. We have like a very large force out here where x equals 0.15 meters. We have a very large force of, I believe, negative 30 newtons, I believe it was. Yeah. Yeah, right. And then the mass is pulled in, is moving all the way to the equilibrium, where at which point finally the force is teeny tiny, it's negligible, it's nothing, it's zero, right? So we've got this force that's changing all the while. When we have a displacement that's large enough for the force to change, what do? Like, how do we multiply force times displacement? We have all these different forces. What we do is we deploy superposition, a principle, which is actually a principle. And like all good principles, it sort of sounds obvious when you say it, but it turns out to be very, very fruitful, and in fact, not, and just false enough of the time that it's worth saying when it's true. We say that when it comes to forces and displacement, we believe that the whole is equal to the sum of its parts. Like, duh, isn't it? Well, we believe that the whole is equal to the sum of its independent parts, which is actually not a total duh. That next class or soon. It's actually not always true in life. It's not even always true in physics, but it is true when it comes to forces and displacements. We believe that the whole is equal to the sum of its independent parts, meaning that each little part, that if we want to know what the whole accumulation of some phenomenon is, we take each little part and we ignore the fact that there are many, many other parts, and we just take the contribution from each part and we put them all together and we get a whole. Like, we don't, in other words, we say, we don't think that the presence or the contribution of any one part is being affected either positively or negatively by the presence of all these other parts. We don't believe, in other words, that the parts are interacting. We believe that they're acting independently, so we can superpose all of them and say that the whole is equal to the sum of its parts. It's actually quite a deep idea. And what do I mean by parts in this case? I mean the individual force values that are being applied to each individual little bit of displacement. By parts, I mean each little sub displacement, each little centimeter or millimeter or something that has some force acting throughout it. What we believe is if we were just to add up all those little bits of work that are being done all over those little segments, if we add them all up, each little segment is not bothered in any way or affected in any way by the presence of the other segment. So if we could just get the work that's being done for each little segment and add up all those little work contributions, we would get a total, which is the total amount of work for the whole thing. Like anything else in physics, in the one hand, it should seem totally obvious. If I explain that okay, part of your brain should be like, well, yeah, duh. Like, hopefully, if you think that what I'm saying is so obvious that it's almost like boring or stupid, then I think you get it. On the other hand, please recognize it's not obvious at all. It's not actually a waste of your time, because in fact, not only that doesn't always work, it's not always true in all of physics, to tell you the truth, but B, if it is true here, then it tells us a method. It actually tells us how to go about dealing with the fact that the force is changing for every little bit of this. And I'm going to wrap up momentarily, which will be just a little shy of 75 minutes, but I'm going to say here, what I'm saying is, remember, a little bit of work equals a little bit of force times a little bit of displacement, right? A little force vector times a little displacement vector, let's say, right? The arrows just mean vector, right? That's a little bit of work equals a force times a little bit of displacement. Again, delta means small but finite. How small? Small enough for F to be one constant value, right? So that's our definition. Then I'm going to say, if the whole equals the sum of its parts, then a big amount of work, a total amount of work, should equal the sum. Oh, it looks like math. No, not math. Well, the sum, right? Sigma means sum. The sum from, and don't let this intimidate you, just counting like from 1 on to however high we have to count, of right. All I'm saying here, and again, I'm almost done, and I know people are trying to come in from. I'm almost done, but all I'm trying to say here now, don't be intimidated. Well, here, in fact, all this is saying, I'm just putting math. So again, even if you think you don't like the math notation, please understand that actually what I'm doing now is just taking an English concept and putting math notation to it. I'm not trying to introduce a new idea. I'm just saying, we believe that the whole is equal to the sum of its parts. Then that means if you want to know the work done for some entire big displacement with a lot of little f's acting over that displacement, then in principle, it should be the case that if you start counting, if you take a little bit of displacement, like we're looking at 15 centimeters here, right? But take the first centimeter of displacement, call that displacement number 1. Like, so set your eye clock to look at displacement number 1, look at whatever and I should say, sorry. Oops, sorry. Totally forgot the key point. Right, like set I equal to 1. That means look at for your first displacement, your first little centimeter. Look at the first centimeter. Look at whatever the corresponding F is for that centimeter, like whatever the force is for that centimeter. Well, in our case, in the first centimeter, the force is pretty large. It's around negative 30 newtons, if I recall, right? So what we would do is for that first little centimeter, we would multiply negative 30 newtons times 1 centimeter, that force times displacement. That would be the work done for that little first centimeter, right? We would take that product and we would put it in our bag, like we'd put it in like a tally counter in a bag mentally, right? And then we would set our clock, now set I, the counting index. Right, so I just means it's like a counting index. So now we go to I equals 2. We go to the next centimeter, like centimeter number 2. We look at the force that's corresponding to that next centimeter. So sub 2, right? It's going to be a new number, I don't know, like not negative 100 and not quite 0 yet, but maybe negative, not like negative 30, because it just was for the beginning. And we're not up to like 0 yet, but it's something like negative 29 or something now, right? So we multiplied negative 29 times the meter, the centimeter number 2 that we just looked at. We'd multiply those two together and throw it in the bag, right? Then we would set our counter to number 3. We go to the third centimeter, multiply centimeter by whatever the force is for that, right? And multiply them together, throw it in the bag. So sum of just literally means that. Take all the little products, each product corresponding to each step that you're taking, add up all of the, like, accumulate those steps. For each step you take, there's a certain displacement and a certain corresponding force. This is all accounting for the fact that the force will be a new value for each step. You just take all those products and you sum them up. You put them all in your bag. When you add them all up, like when you open your bag and add them all up, the total you get is the total amount of work for the whole thing. Like as long as we believe that the whole is equal to the sum of its parts, then the work, I haven't figured anything out. I'm just explaining how we figured it out, right? And I'm going to stop in 1 minute. But so work in general would be the sum of all of the little works. The only catch here, and this is where we're going to end. I'm going to write one more sheet and we're going to end. The only catch here is that the force is not jumping in these discrete countable steps. Like we can't literally, like this would be true. This is true if we can do this, but we can't really do this in a case where the force is changing continuously. Because no matter how small we make the x's, the F is still changing a little bit, right? Even if I go 1 centimeter at a time or 1 millimeter at a time or 1 angstrom at a time, there's still variation in the forces. So what we want, and this is the last thing, this is what we want. We want to take that process of counting. We want to take the sum of products to the limit. We want to divide those little sections, those little steps, into such small parts that each delta x is infinitely small and there's an infinite number of them, so that we can account, right? So that we never skip any steps at all in this variation of f. We want to take the sum of products to the limit as the number of products approaches infinity. That's what we want. I'm not saying how to do it yet. I'm not saying that we have done it. I'm going to end right there for now. That's the whole video. We'll pick up, please. Well, you will have watched this by Wednesday. We'll pick up from there Wednesday. Just leave it at that. So I haven't answered question 4 yet. We have to get to answer quick, but just leave it there for the moment. That's where we are. Thank you very much for watching. You're the best. I will see you very soon.